All right, we're going to prove this theorem here that P if and only if Q, or that P is equivalent to Q. P and Q are equivalent statements where P is the statement that G is disconnected, and Q is the statement that there is a way to label the vertices of G so that the resulting adjacency matrix is block diagonal. Remember, to prove something of this form, P if and only if Q, we have two things to prove. We have to prove that P implies Q, or if P then Q, and we have to prove that Q implies P. If Q, then P. In this video, I will prove the first of these, that if P, then Q, and in the next video, I'll prove Q, if Q, then P. So let's begin. So we're going to prove P implies Q. Remember, to prove if P then Q, you assume P and show Q. So we will assume P. That is that G is disconnected. So I'm going to start up here for the sake of saving some room. Assume G has disconnected subgraphs G1 and G2. Now these are these subgraphs G1 and G2. They are graphs in their own right, and so they have some amount of vertices. So we can assume that G1 has M vertices. And that G2 has N vertices. Remember the little v of G1, that's the number of vertices. And we'll assume that M and N are positive integers. All right, so I'm going to label the vertices V1, V2, all the way up to Vm. And I'm going to label the vertices of G2 Vm plus 1, Vm plus 2, all the way up to Vm plus n. Now before I go on, let me explain what I'm doing here. So let's, for an example, let's say that G1 is this graph, this subgraph of G, and that G2 is this subgraph. So in this case, M, the number of vertices of G1, is 4, and N, the number of vertices of G2, is 3. And so because G1 has a finite number of vertices, I can just pick one of them to label V1. I can pick another one to be V2, V3, and V4. And now I don't want to reuse these labels for G2 because that would be confusing. So I want to use a new label. Since M is 4, right, M plus 1, 4 plus 1 would be 5. So I'll label this one V4 plus 1, otherwise known as 5, V6, and V7. And notice that V7 is in fact M plus N. M plus N is 3. Or N is 3, M is 4, so M plus N is 4 plus 3 is 7. That's exactly where I get that 7 there. All right, so that's what I'm doing in general. Right now. Okay. Now each of these subgraphs, G1 and G2, are matrices in their own right, or are graphs in their own right, so that each of them has an adjacency matrix. So we can assume that, so we can give a name to those matrices. So assume A1 is adjacency matrix for G1, A2 for G2. All right, so then the adjacency matrix for the big graph G that has the disconnected subgraphs G1 and G2 is this graph. Or is this matrix? I apologize. I meant to say matrix. And remember, we can think of these as, we can think of an adjacency matrix as a grid that displays the adjacency or edge information. All right, so it's going to have this form. Now, since G1 has vertices V1 to Vm, and A1 is the adjacency matrix for G1, A1 contains all of the adjacency or edge information for the subgraph G1. So if you think about the way we've labeled these things, right, we've labeled them V1, V2, all the way up to Vm, and then Vm plus 1, Vm plus 2, all the way up to Vm plus n, right? So V1, Vm, and then here we'd have V1, Vm, it's the adjacency matrix A. Okay, so A1 has all of the adjacency or edge information for G1, and that all happens with vertices V1 to Vm. Right, and so that's why in this part here corresponds to G1. This is the information for G1. And similarly, this is all of the information for G2, which because we've labeled all the vertices, vm plus 1, vm plus 2, all the way to vm plus n, we have all of that information is contained there. So now we want this thing to be block diagonal. Remember, that's where we're headed. We want this matrix to be block diagonal. And that's only the case if B1 and B2 are all zeros. So that's what I'll prove now. So I'll state this with a claim. My claim is that first for B1 is all zeros. And to prove this claim, I'll use contradiction. So what we'll do is we'll say, suppose that A I j equals 1, where I is between 1 and m, j is between m plus 1 and m plus n. So that means that there's a 1 in here. So now see, I between 1 and m, right? That means that I is somewhere between 1 and m, right? And remember, we do rows and then columns, and then j is somewhere between m plus 1 and m plus n. So that means that there's a 1 somewhere in here. Right? Now, what's the problem with that? Well, we assumed that G1 and G2 were disconnected, right? So I being between 1 and m, that means that VI is a vertice in G1. And j being between m plus 1 and m plus n, that means that Vj is a vertex in G2. But then see what happens? If those are connected with an edge, right, then, so let's say, so this happens. So G1 and G2 are connected. This is a contradiction. This is a contradiction because we assumed that G1 and G2 were disconnected. And so that means that these are all zeros there. Similarly, B2 is all zeros. Right? A very similar argument can be used to show that B2 is all zeros. So the adjacency matrix A is block diagonal.